The following information applies to problems 21 and 22. Water flows through a pipe with a radius of 5 cm at a velocity of 10 cm per second before entering a narrower section of pipe with a radius of 2.5 cm. Problem 21. What is the difference in the speed of water between the two pipes? Solution to problem 21. We assume that water is incompressible. Therefore, A1V1 is equal to A2V2. Here, A1 and A2 are the cross-sectional areas related as squares of the radii. Then V2 will be 40 cm per second. And the difference V2 minus V1 will be 30 cm per second. This is answer B. And this is the solution to problem 21. Problem 22. To measure this difference, two graduated cylinders are connected to the top of the pipe, one in the broad section and the other in the narrowed section. Water then flows up each pipe and the height the water reaches is measured. Estimate the difference in height between the two cylinders. Solution to problem 22. Using Bernoulli's law we have equation 1. Hence the height difference will be as in the expression 2 or 7.5 mm. This is the answer B. And this is the solution to problem 22. Problem 23. The student conducted an experiment to determine the spring constant of a spring using a ruler and two different weighing scales. The measured elongation of the spring was 1.5 centimeters, and the smallest division on the ruler was 1 mm. The mass of the attached weight was measured using two different scales in the school laboratory, yielding values of 198 gram and 210 gram. The student also found that the local acceleration, due to gravity in her city is given as 9.806 plus or minus 0.001 meters per second square. Calculate the percent error in measuring the spring constant. Solution to problem 23. The relative measurement error of the spring stiffness is calculated as the root mean square measurement error of all three independent parameters. The length of the spring, the mass of the load, and the acceleration of gravity. Since K is equal to mg divided by L, we have a simple formula. Here delta L is the measurement error of the ruler, that is, 0.5 millimeters. The measured length L is 1.5 centimeters, delta M is the measurement error of the mass will be the difference in mass in half, and the mass M is calculated as the arithmetic mean of two measurements. And for G, we have an error of 0.001 meters per second squared, and G itself is 10 meters per second squared. As a result of simple calculations, we obtain a relative error of 0.044. Which is closest to the answer B. This was the solution to problem 23. Problem 24. A massive bead is attached to the end of a massless rigid rod of length L. The other end of the rod is attached to an ideal pivot, which allows it to rotate frictionlessly in any direction. The rod is initially at angle theta to the horizontal, and there is no gravitational force. Next, the bead receives an impulse directly into the page, giving it a speed v. How long does it take for the bead to return to its original position? Solution to problem 24. No matter what theta is, the bead always moves in a circle of radius L. The total distance it has to travel is 2 pi L, so the time is 2 pi L over v. This is answer A. And that was solution to problem 24. Problem 25. A puck of mass m can slide on a frictionless inclined plane, prism. The prism has a much greater mass, compared to the puck and is itself sliding without friction on a horizontal surface. The velocity of the prism is v equals square root from 2gh, where g is the acceleration due to gravity and h is the height from which the puck starts sliding on the prism. The transition from the prism to the horizontal surface is smooth. The puck starts from rest relative to the prism. Find the final velocity of the puck once it begins sliding on the horizontal surface. Solution of problem 25. This problem is easiest to solve in the initial rest system of the prism and the puck. Then, by conservation of momentum, we have expression 1. The mass of the puck m small multiplied by the final velocity of the puck v1 is equal to the mass of the prism m large multiplied by the final velocity of the prism. Further, by conservation of energy, we have expression 2. 1/2 m small by v1 square plus 1/2 m large v2 square is equal to mgh, which, by conditions, is equal to 1/2 of m small v squared. Solving these two equations with respect to v1 we obtain formula 3, that with small m much smaller relative to m large is equal to v. Going back to the original system we obtain formula 4. The speed of the puck is equal to 2v. This is the answer E. And this was the solution to problem 25.